So anyway, let's get right to it. So yeah, we're going to be discussing graphs and networks in the Wolfram language. So let's get right into it. So just going to give a bit of an overview of what we're going to talk about today. We're kind of going to go into the essentials about defining what graphs are and kind of some example network models. So these are kind of basic things. So what we mean by a graph, and then kind of tailoring that to how we can specify graphs in the Wolfram languages, how we can specify edges and vertices, weights, etc., etc. So within the Wolfram language, there's a bunch of different ways we can specify those graphs. So we'll look into those, how we can actually build graphs from data, from various different data formats. Also, another big part of the webinar is going to be like the kind of appearance options for the graphs, so how we can style them in particular ways. Wolfram language is very flexible in the way you do this, so we'll look at a bunch of different ways we can do that. And also, so kind of some of the operations, properties, and measurements we can do. So, with graphs being very symbolic in nature, we can kind of augment them, play around with them. We can do a bunch of different stuff on them. We can do a bunch of different, some things, including simple basic things to more global, like graph theory concepts. Also, you can do general calculations, so involving distances. We'll look at some large graphs, how you can work with large graphs in Wolfram language, and then we'll finish up by trying to solve some actual graph theory problems, kind of showcase off Wolfram language being pretty cool to do a bunch of different stuff in a very minimal amount of code. Okay, let's get right into the fundamentals. So what do we actually mean by a graph? So when we talk about a graph, this is kind of like this computer science concept where we are talking about an object which has, a series of, nodes or vertices, and then relationships between those nodes, and we call those edges. So this is a very abstract thing in definition and can really mean many, many different things. It can be related into fields of study within computer science. So talking about database design, data mining, web mining, etc. We can kind of represent social networks. We can represent networks to do with physics, ecology, economy, and all sorts of different things. It's a very powerful abstract concept to be aware of because it really does have relations in all sorts of fields of study. So it's well worth being aware of this and being able to use it. Makes you a more proficient Wolfram language user. So graph objects in the Wolfram language. Let's actually look at some of these. So here I've got a representation of a graph, and we've assigned it to this symbol here. And this is one representation, but if you want to have a look, peek under the hood and see what it's actually looking like, you can use this function input form to go in and kind of explore how it's being generated. And it's just really like this representation here is just like any other Wolfram language function. So we should be able to evaluate that to get the same thing. And this is pretty I think if you change the size here, then that's going to be represented in other ways. Oh, if we did this, if we made it bigger here, then we can change its directly maps to the image size here. So this input form peeks into the example graph at that given time, and when we change the input the size of it in here, that's going to be seen in the input form. So input form is a powerful function to be aware of. It kind of, as I said, it can let you peek into what an actual symbol is looking like, and how it's actually being created. So definitely be aware of that. So also, some fairly fundamental things. Graphs in Wolfram language are atomic. We can query this using AtomQ. So, graphs in this sense, because they're atomic, they are not dividable. So, whereas lists are, something I can do part extraction on, a graph like, what was it called? The graph we just made, if we try and go into that, it's not going to work because it is atomic. So again, I would be look into all these different kinds of Q-related functions, which can give yield like a Boolean true or false, dependent on a particular expression property. So here, if it's atomic, then it's going to yield a true value for that. So because they are atomic, you need to use special functions to actually kind of extract the kind of important meta information related to them. So things like, if I want to get the list of vertices, edges, some of the options involved to the graph, then we're going to have to apply these special functions to kind of extract that out. And if we kind of map them over this example graph, then we can extract out these useful properties to kind of gain graph-related insights into our example graph here. All right, cool. So how can we actually specify a graph? So probably the most simple way of doing it is just specifying a list of edges in a graph. And there's a bunch of different ways you can do that. So we can create an undirected edge by just using the undirected edge function, or we can just use the directed edge function. So pretty unsurprisingly, it is just directed edge. So in these graphs, edges will connect to vertices. And actually, I should probably mention, so that you have this distinction between directed edge and undirected edge. So directed edge kind of implies there is a direction involved pointing from one node to the other one. Undirected edge is the inverse of that. Again, more ways we can specify that. So we can use directed edge. We can also use this kind of shorthand form here. So if I type it out with square bracket directed edge, then we can create this object here. And then I should be able to just square bracket. That's not that. Yep, so I can create a graph here. I can also put it into a list. So I can, give it some more information. Let's go 3, 2 to 2, 2, 3. So yeah, we can kind of like construct this more and more, adding more information to create our graph object. We can also use rules to generate the notion of directed edges, which are important constructs in Wolfram language. That kind of represents a mapping of one value to another value. So that's definitely something to be aware of. Also, so one distinction to be aware of is so directed graphs. So a graph object can have both directed and undirected edges. But so two complementary directed edges are going to be distinct from an undirected edge. So in this case here, we've got a directed graph where we've got a mapping from 1 to 3 and 3 to 1. That's actually distinct from having an undirected edge from 3 to 1 here. And so you can actually query that using directed graph Q, which is similar to these Boolean true false Q type functions in the Wolfram language. So it will query a property about an expression, in this case directed graph and hybrid graph, and then given that expression's intrinsic value, it's either true or false for this given property. So again, kind of just like fermenting, confirming that concept. Directed graphs are not the same as hybrid graphs. So we're using graphplot. You can actually specify a bunch of rules here. We're mapping start to none using these the rule notation here, and then we can throw that into graphplot and then we can, generate a graph in another way, in this other format where we're kind of predefining the rules beforehand. So it's just kind of like a useful way to kind of introduce this graph concept. And then we're throwing in a bunch of plotting options. So we're giving it a specific theme, we're giving it specific labels, and we're telling it to be a large image. So it's just kind of a useful way. If you have predefined rules, then I only have to change it in one place. If I'm gonna create a bunch of different graphs for a given data set, then I can do so like this. What did I miss initially? Not very much. We just went over some graph introductions, but I don't think you're going to miss out too much. Okay, so edges and vertices. So you can specify a list of vertices and also edges to allow unconnected vertices. So let's have a look at that. So here we've specified a graph of these 5 points. We've also got 5 and 4 here, which is not, it's in an edge which is not connected to anything else. So by doing this, we kind of get this separate graph object. Also, we also have this mapping of one value to another. So this is generating a loop in our graph, where it's kind of going from one point and then back around to itself. So that's how you introduce loops in graphs. So the kind of symbolic nature of the Wolfram language allows the vertices to be any expression at all. So here we can use an image, a integer value, a string, an actual graph itself. So in this sense, we can kind of nest graphs within graphs, which is kind of cool. So here we've got the image, we've got the string value, we've got the integer value, and then we've got a graph. So we've got a graph within a graph. So that's just the cool part about symbolic programming. Everything kind of is interpreted to this uniform expression structure. So you can kind of throw things in, whereas in other languages you're going to struggle with that. So that's a very powerful property of symbolic programming. So we can also set weights in graphs. So this is a important concept to kind of query a relationship between two nodes and give it like a specific parameter. So it might be something like distance, it might be connectivity. It can be very, very representative, and like being aware of this, you can represent a lot of different things. So here we can use vertex weight to do so, and then we are plugging in the vertex weights themselves. I think this is really important. I think this work is really important for graph neural networks. Yep, I think it will be important for graph neural networks. Okay, so this is how you specify weights using the weight function. You can kind of throw it into graph. Also, I would recommend checking out all the options available in the graph function. It's a pretty powerful function. And so we can also label them with specific edge weights and vertice weights, and then add on these individual directives. So I think this is just, it's just giving it a particular color. So that's kind of how we're specifying it. We're also specifying it here to be red for the label style, and then for the edge label style, we're just giving it a blue font over there. So we can specify graphs in different ways instead of just using the graph function. We can also use adjacency matrices. So these are going to be like n by n matrices, and in the simplest format, we're going to have a 1 representing an edge from vertex I to vertex j, and a 0 to represent the absent of an edge. So we can do that. We can just create this matrix here. We can have a look at it in the matrix form, which is a little easier to understand. And then we can kind of like convert between the two to kind of create a graph object from a from a matrice. So like so. So we take this this matrix here, and then we plug it into adjacency graph to create this graph representation as we've seen before, but coming from a matrix this time. So it's nice to have this interoperability. Matrices are very powerful in other forms of computer science. If you're doing anything linear algebra related, it's going to be a powerful thing. Okay, so we've got this. So if you peek into the adjacency graph here, this is actually, if you try and get it into, if you want to go from adjacency graph to a matrix, you have to do something a little bit separate. So we've got our original adjacency graph, which we generate here. If we want to turn it into an adjacency matrix, you can't just throw on adjacency matrix onto the graph. You're actually going to have to go, because the adjacency matrix reveals a sparse array. We're going to have to kind of unplug that a bit, because a sparse array is like a bit more of a lower level data structure in the Wolfram language. So you have to look at it through the normal to get to the actual raw values. And then from that, that's when we can turn that list into a matrix form. So that's how you go from adjacency graph to a matrix. Okay, this should probably hide this. Okay, so when we're going from more matrices to graphs, just some kind of like simple graph theory concepts. When your matrix is symmetrical, so it's got a line of symmetry along the this line here. When it's symmetric, then it's going to be a directed graph. But that's not the case for when it does not have a line of symmetry. Instead, you get this undirected graph. So where things are looking a little bit different, and you've got these directions involved, whereas you've got a like pretty universal traversal order here. Okay, so let's also look at weighted adjacency matrices. So you can also create a graph using a weighted adjacency matrix. So similar to like where we were before, we had zeros and ones representing relations between each other, between nodes. If you want to like plug in some weights to those, some weight parameters to represent like querying things that could be any type of relationship. Distance was one we were thinking about earlier. So to do that, it's a little bit different. Instead of using zeros for the absence of a relationship, we're going to use the infinity symbol. So I guess like this does make a little sense if you think about it. So it takes, if we were thinking if we were talking about the relationship to be distance, if something is an abstract value of 2 away, it is you can get there within 2 steps. If it is an infinitely long way away, then it is effectively impossible to get from node 1 to 1 or 1 to 3 in this place here. So again, we can use these Boolean true false querying functions. Is my matrix here a symmetric matrix? And yes, it is. We can then go ahead and create the weighted adjacency graph from that matrix. Here we're throwing in just some general plot options. So I guess something cool to be aware of. This is an icon. So if you want to like kind of embed data or options or anything really into a notebook, you can just use this iconize function, so that it's just kind of ready to use format for if I had a like large data set and I wanted to store where I was in a particular process, I could iconize it, save my notebook, and then look at it later. Here we've kind of just iconized some general metadata to do with plotting options. So here we've like distinguished a label style into this format here. So it's just a little white triangle, white square even. But yeah, that's something to be aware of. Pretty useful part of Wolfram language. Okay, let's look at another weighted matrix here. Again, we can query it with these Boolean true false values. In this case, there is no line of symmetry between the kind of where the points are the same, where vi is vj. And then we can go ahead and do the same thing. We can get a weighted adjacency graph from here. Because it's not symmetric, then we get this directed graph. So I think if we do like directed graph q, then we can query that. Yeah, we can get that here on this object. So just kind of like a graph theory concept. Symmetric graphs are directed. Yep. Oh no, so yes. So this is a, oh no, this is not a direct, this is a symmetric, this is not a symmetric graph, so it is directed. My apologies, I got that mixed around. Okay, so let's have a look at some incident matrices. So here, a vertex is incident to an edge if it is one of the vertices to which an edge is connected. So we can kind of represent that in, again, in a matrix form, where you've got an incident matrix where you've got n by m, and then a row for each vertex and a column for each edge, where, position 0, we're not going anything, and then we've got a few more to represent these incident matrices all together. So we can go ahead and create a matrix, and then we can go ahead and create a graph from that matrix that we've just explained here, and then we can throw in some more plotting options to kind of generate this incident graph. So representing all that information. If we want to go ahead and pull out the edges in that incident graph, we can just query it using the edgeless function, which is just pretty simply getting out all the edges. And then we can again go from a incident graph. If we want to turn it into a matrix, then again we're going to have to query it through this kind of lower level format, getting it into a sparse array, into a list of numbers. And then finally, we can return it back into a matrix. Matrix form, that's the one. Cool. Okay, so within the Wolfram language, there are many different kind of named graphs. So nice. One of the nice things about Wolfram language is the kind of intersection with like a massive knowledge base, and this goes for like many different fields of study, not just graphs. But within graph theory, there are many named graphs, and the nice thing about the Wolfram language is you can kind of just it's kind of got that baked into the system. So we can just create a bunch of different, if I want to create a Peterson graph, there is a function, a pre-existing function for that. Also, some of them are going to be coming from a, I think. So here we've got graph data, so we can pull in a different graph. I think we've got a bunch of different graphs. So yeah, we have a bunch of different named graphs. So to do with a given vertex number. So if we have, how many graphs do we have with 10 points, we can then query that. So okay, there's quite a few. Let's maybe give it something a little less exciting, maybe like 5. Okay, and then with that, we can then query that using graph data to pull in a banner graph. So let's have a look at that. And then, yeah. So cool thing, it's just a nice intersection if you're working with graphs of a particular field of study. So, we could have a lollipop graph. There's a bunch of different things baked into the system. And you're just it's very easy to query that, pull it in, and then work with it, or get a better understanding of in this case a Pappas graph. We could do some of those functions we made earlier, and then we could augment them more. Also, so other than those like kind of baked in graphs we have there, we can also we have example example data here. So, if you're looking to do some, one thing that comes to mind, there's loads of example data sets. So if I want to, build an ML classifier, I think there's example data. I think it's just literally machine learning. So I wonder if it pulls up an example here, or it might just crash my system. That was a bad idea. Oop. Okay. I shouldn't have done that. Okay, I'm not going to do that again. Never mind. But yeah, so you can pull in machine learning data sets, and then I can build like an ML classifier. In this case, we're just going to look at a network graph about books of US politics. And then I think I can, again, look at the edge lists. And then I can look at these individual books about US politics. So there's a bunch of different ones. This is a pretty big graph, but it's just kind of baked into the system. You can play around with it, learn more. It's just a nice construct to be able to take starting data and then go and do something with it, doing some graph computation with it, which is all pretty interesting. So if you want to go ahead and instead of like rely on those pre-made graphs, we can actually just make graphs. And we can use random graph to do that, to kind of simulate networks according to specific distributions. So here I'm going to make some random graphs according to these distribution parameters. I think these are going to be like mean and, I don't know, represents a uniform graph distribution of the number of vertices and number of edges. So you're kind of creating these pseudo-random objects. This is going to be useful for simulation type works, and you're not related. You're not held back by just using uniform graph or Bernoulli graph distribution. There's a bunch of different ones. So let's have a look at this one. Okay, so we're just getting a graph distribution, so we could throw that in here if we wanted to generate some more things coming from this map object here. What was that, like 21, throw in some parameters, and then we generate a graph object here. So again, you can do that in this thing. If you haven't seen this before, this is just map notation. It's just going to be the same as, if I wanted to do it over this, it's the same. It's just shorthand form, but it's a nice thing to be aware of. Can shrink down your Wolfram language code and just be a little bit more terse, which is kind of nice. Okay, we can also kind of, Wolfram language, we kind of support many different type of graph formats. So the graph, we can import them from, graphlet dot files, graphml, GXL. I know we also work with RDF type objects. So, there's many different types of import formats. That's the kind of like nice versatility of the Wolfram language. You can query it with this $ import formats. But yeah, you can do a bunch of different things here. I can just like import this example graph object. I can then even throw into the import some plotting options. So if I wanted to increase the padding, I could do so just within the import already. So it's just a nice like streamlined process. I'm only doing one line of code, and I'm doing quite a lot here. So very powerful. It's the powerful terse nature of the Wolfram language. I think Sparkle. That's another Sparkle query. So you can kind of work with many different types of graph objects. Okay, so again, like Wolfram language being symbolic lets you do some cool things where data isn't necessarily in a standard format. Say we've got an image and we want to convert it into a graph format. You can actually do that pretty simply. That's a nice, pretty powerful. In Wolfram language, you've got a bunch of different image related functions. So if I want to negate it, I want to binarize it, thin it, prune it, delete small components. These are all things to do with specific image, kind of like image augmentation, image segmentation, I believe. You could also do this with, if you are looking at like images of cells. I know that's kind of big in kind of biosciences. I can kind of binarize images of cells to kind of do the counting for me in this nice format. Potentially feed that into an ML neural network. Okay, so I can then kind of use this morphological graph function on this binarized function here, and then rasterize that image. For every node, I'm going to create these lights. Yeah, so every shape, we're putting in this little image here for at every node. We are putting in some traffic lights. So presumably this is looking, trying to get an insight of the location of traffic lights in Champaign, which is the location of the American office, main Wolfram HQ. I'm currently streaming from Oxford in the UK. But yeah, it's just kind of cool to see, we started with an image, then we did some pre-processing of that image here, kind of plugging it in as if it were raw data, and then augmenting that in such a way that I can create this nice graph object here. So kind of creates a, for a given image, we create a graph representation, which is going to have the input form. If we have a look at the input form of this, so under the hood, it is a graph object. So that might take a while because it's really big. But yeah, that's kind of the concept. Okay, it's actually rendered as an image, not a graph. But under the hood, it will be using, I think this rasterize is throwing it off. Okay, right, let's look at some styling options. So, these are somewhat self-explanatory, really. You can kind of augment particular edges to, in this case, we've just got a simple graph of, a bunch of edges. Say I want to throw in a particular edge here. So here we want it red and thick for 3:1. Then we can do that. Let's look at the vertex labels. Goes to name. Get that a bit clearer. So yeah, 3:1 here. We've labeled that, with this red style. So I think we could also, change that up. If I want a blue, purple, somewhat, self-explanatory. Let's have a look at larger. Wonder what that looks like. Oh, that counterintuitively made it smaller. Okay, but yeah, you can throw in style options into the edges themselves. Also within the actual nodes. So here we've labeled node 1 to be yellow, but we can. There's a lot of variance within that. Also, so we can also kind of group them together. So if we want the vertex style to be green here, we've kind of plugged that in here to make them all green. So X vertex style green. I think that might overwrite some of them, except for the ones that we've already pre-labeled yellow. So if we just put that back there, then you can kind of, the vertex style doesn't override the initial ones you've plugged in here. Again, we can throw in using these directive functions that we want it blue, thick, and dashed for our edge style. And again, we could throw that in to here to get another one. So let's make it purple, thin. And then, yeah, it's very, augmentable. You can kind of query it. You can change it to the way you want. It's a very nice way of being able to, tailor it to how you want it to look. You can also define the vertices and edges in terms of functions. So if I want to, here I'm just pre-making a function for given xy coordinates and a bunch of other meta parameters, then I'm going to make a disk for them, or I'm going to give it arrowheads. So it's very you can kind of you don't have to repeat yourself giving specific labeled parameters. So here we're really labeling the parameters, but here we can instead kind of encapsulate that in a function, feed it into like vertex shape function, and then every time we make a graph, then we create a new thing. So I think this has some like variance within it. So every time we make it, we're calling this function. It's not going to be the same. It's going to it's throwing in a random integer for this edge shape function. So it's kind of like just a nice, gives a reusable element to the graph function. Also, there's predefined stars within it. So if I want that to be square for the vertex shape function, I'm sure if I add a circle or a triangle, there's these built-in vertex shape functions. In fact, there might even be things that you can define your own in terms of patterns, or use the pre-existing ones, which might be to do with squares and a bunch of different things. Okay, so there's also some kind of internal functions to do with graphs. So we can also list of all the predefined edges, and so we can kind of create these. So this is just showing off all the built-in vertex shape functions. So this is going into the graph computation context and then extracting out anything to do with vertex shape functions. That's actually what I was looking for. So let's have a look at what concave diamond looks like for this. Okay, so there's a bunch of different variants, kind of like of these built-in things for the edge functions. Okay, it doesn't like that one. Okay, let's look at some edge functions, which are here. Edge shape function. And I'm sure this will show me a very beautiful carved arrow here. Maybe not. Okay, so I think there's just a bunch of them. So some of them might work, but the internal nature of it means it's not documented. Okay, so within your graphs, you've got you can give it a certain plot theme, and for a given style. So this is just a nice graphic to show off all the different kinds. So if I want my graph object that I'm making here, let's give it a different plot theme. Plot theme of what's one I know? Minimal. We can throw that in here, and then options expected instead of null. Okay, we've got 2 commas there. What's wrong here? Let's get rid of this actually. Okay, there we go. Minimal. So yeah, you can just throw it in, and these are kind of like all pre-built for you. Some of them look pretty good actually. I think for me personally, I would just, if I'm making graphs to show off, I usually just use the built-in stuff. But you also have that like nice ability to kind of make your own function. But usually I'm just using these built-in things that look pretty good. And we can also throw in particular color schemes, and these are kind of like predefined to make it look good. You can also vary the vertex shape. So here we've got a list of edges, and because nicer interpretability of the Wolfram language, it kind of infers the vertices from these given edges, and then we can give vertex shape to we can kind of give these rules where instead of 1, we want this hexagon, instead of 2, we want this lovely sunflower here, and 3, we have this lovely, I don't know what that is, but shape, you know, and then we can kind of throw them in. Cool. Okay, let's also, so we can also kind of label these in many different ways. You know, this is somewhat self-explanatory, but you know, if I have my list of nodes and I want to label it, I can label it, you know, instead of A, I could label it something like hello. Then we can kind of query it here in many different ways. Again, we can label the edges. So again, if I want to, you know, let's throw in hello again. And then we've got the vertice label from 1 to 2. And then, yes, we get a bunch of different ways we can do that. It's probably not the best thing to show, actually. Okay, cool. But yeah, basically you can just label, you know, any single point or edge like that. And so, okay, so if we want to label 1 to 2, then we can label that 1. So let's label it. I think it's pretty, yeah. So we can turn it into hello. You know, you can kind of throw anything if you want to augment your initial thing. Okay, you can also, you know, for vertex labels and edge labels, you can kind of predefine it using indexes. So these are the specified named values of our object. So yeah, we can throw in pretty much anything we wanted to. Here I'm just throwing in the index of the vertice. Okay, so we can also kind of like play around with the layout of objects, of graph objects. So here I'm just going to set up this simple map function and then put it into a row. Here I am just plugging in. So we can define edge and vertex layout using vertex coordinate. Here I'm just going to plug in automatic, or I'm going to give some explicit instructions on how to create this object. And we're just using complete graph. So we're just giving a complete graph with named vertices. And here, you know, it's kind of specified, you know, here I just wanted it to plug it into automatic. But here I have plugged, in this case, I have plugged in, here in this place, I've plugged in this explicit kind of coordinate system so that it looks like this. You know, we're just throwing this into a map, and then this is just a pure function, and here's the slot for these two elements. So there's also a bunch of different ways you can kind of look at your, like, view the embedding of a graph, a bunch of different like built-in ways of viewing it. So here we've got I've got a simple graph, and then we can kind of rearrange the way the graph is looking. So this might be useful for getting particular insights into, you know, different graph formats. So these are all built in, and I think we're just plugging in, so graph layout. So I feel like we could, if we wanted to have a look at, so let's see if we can plug this in here, and then what was it? Graph layout goes to Spring electrical embedding. So, you know, it's just rearranging the way the graph is formatted. I think because we're plugging in these explicit vertex coordinates here into this second one, then it is kind of overriding the graph layout, the embedding itself. But yeah, you know, you can plug these in, change the way the graph is shown, and then this kind of is kind of going into, you know, a bunch of different ones for a given graph. So it might be a nice way to rearrange your graph to see it in a different format. And some of these have like intrinsic properties. So spring electrical embedding kind of matches the length of edges to correspond to their weight. So it kind of gives this nice visualization of the graph and kind of like rearranges the visualization given particular graph properties such as the edge weights. And some common layouts have their own plot functions. So let's pull back and see what this is doing. Okay, so yeah, we're just looking at the different kinds of plots for the graph. So you can also throw on different wrapper functions. So here we're kind of giving interactability. So dynamic modules, pretty powerful within Wolfram Language. I think this just lets me change the individual styles. Dynamic modules are kind of similar to if you've used React. It's kind of like use state, kind of like lets you update variables in this interactive format. So this is kind of similar to how you do that in the Wolfram language. You'd declare this dynamic module and then our dynamic variables, which we want to potentially change during evaluations, and we can give them baseline pre-existing formats. So here we did it green, and then if I want to change that, then I can click at it, and then this is what we're doing. We've got a button, and then when we click this vertex, then it's going to update the dynamic module into a random color, which should just evaluate every time. And then when we click it, it will call that dynamic. It will update that dynamic variable into a bunch of different formats. Okay, so when you create graph objects and you give it specific like properties, then when you call subsequent graph-related functions like find spanning tree, then the pre-existing vertex, edge, and labeling options that we've kind of predefined will be inherited from subsequent objects. So here we've kind of got this Peterson graph. I think it's kind of got a specific labeling system. I think if we look at it in the normal format, which is how it is, this is how it is before, then we've thrown in a vertex shape function, some edge weights, and then told it to be small. And then we've assigned it to this symbol here. So when you call subsequent graph-related functions like find spanning tree, then the options which we specified here are going to be inherited from subsequent calls to this graph. It's not going to go back to how the baseline Peterson graph is created. And we can also take the augmented object, the augmented object. We can then throw on extra styling options. So if I wanted to make it blue, the edge is blue, I can do that also. So we can also render 3D graphs using Graph 3D. So here we are just generating a complete graph with 4 vertices. We can then go ahead and look at that in 3D if we so desired. Sometimes this can be a little computationally expensive. So if you're struggling to render it, I would just stick with the 2D variant. Again, it's this graph plot 3D accepts matrices. So we can kind of take this matrix here, and then we can go ahead and plug it in and then plot it into this 3D format. So yeah, because of the 3D nature, there's quite a lot of rendering going on. I'm on a pretty powerful machine right now, so I can just about handle it. But yeah, if you're running into performance issues from graphs and you're using Graph 3D plot, it is worth just pulling it down into 2D to make it a little bit simpler. think this is throwing an error because you can't have spherical regions in 2D objects, which fair enough, that makes sense to me. And if you want to have a bit of a smoother result, then you can convert edges to lines and vertices to points for a little bit easier rendering. I think this looks like it's a little less going to be a little less resource intensive than having a 3D image. We've got this pretty chunky balls here. And so yeah, that looks a little easier to represent quite a lot of information. Okay, so we can kind of extract out some graph properties measurements, and we can do a bunch of operations on our graphs. I'd recommend checking out this this tech guide. This is pretty helpful for kind of looking at what I've just talked about, but in a little bit more detail, and kind of lists all the related functions. Okay, so let's make a complete graph with 3 vertices, and we can manually modify this graph object here. So I can delete particular edges. So I can delete 1 to 2 here and create a new format. I can also kind of contract so if I make another graph here, I can kind of contract the edges to collapse down the graph object into a smaller format. So here I'm contracting, getting rid of 1 to 4, kind of merging them together. So when I do that, it kind of pulls it in, removing that edge here, kind of contracting the object into that format. And similar with 2 to 3, what was that? We can kind of contract that down. If you think of it like pulling it in together, merging those 2 nodes together so that we just get the 1 node, and kind of just this kind of showing the manipulability of the graph objects themselves. Again, symbolic programming at its finest. Okay, so you can also convert graphs using higher level augmentation graph augmentation functions. So, and these are kind of a little bit higher level in the sense that they're doing a lot more with a little thing. So here we're looking at a graph here, we can just remove any self loops here. So if we look at a little initial graph object here, I can then call simple graph on it to remove any loops. I can reverse the graph to presumably reverse the graph, reverses the direction of all undirected edges. I can have a look, I can create all edges to directed edges, etc., etc. So these are all ways you can kind of just take a graph object and then turn it into a directed graph. But yeah, you can kind of just plug it in, this kind of symbol here, into the directed graph function, and then generate the output here. Graph power. Interesting. Combining graphs. Okay, so you can kind of also merge graphs together. So here we've got 2 graphs. You can kind of use these combination graph functions. So I can get the intersection, union, graph difference, and again, I'm presumably just throwing in the 2 graphs together. So this graph. Oh, this hasn't been separated out. So I think this image is already consisting of both images, so I can't just call that function. But I think presumably you just need to take 2 graph objects and then take 2 graph objects like these 2, and then if I wanted to get the graph intersection, I can do so I've got these of G and H. I can then go and create an intersection of the 2 graphs, so where they kind of intersect. And so yeah, usually these combination graph functions are going to take 2 arguments for the 2 graphs you're looking to combine. Again, you can kind of get Boolean type operators into your graph, into both your graphs. Okay, cool. Let's look at some more properties. So let's look at we've got a complete graph here. If I want to extract out some information, I can do things like vertex count, edge count, just general graph meta information. I can get out the vertex list, edge list. There's a bunch of these graph queue functions. So let's see here. How many are there? Oh, that's looking. So yeah, there's a bunch of different querying ability. This is also just a nice. If you want to learn more Wolfram language functions, then do question mark and then asterisk. So anything beforehand, and then what network functions do we have? We can look at network packet capture. But yeah, it's just a cool way to work out different Wolfram language functions. So things that are ending in GraphQ. And then the asterisk is a wildcard character, so anything preceding or post-seeding an initial symbol. So there's a bunch of different graph property querying functions. I think there's also going to be loads of graph functions. So these are the looks like the kind of graphs we can make. So yeah, many different types of graph functions. Some of them, again, is it a complete graph? Is it a simple graph? We can query that all very easily. And I think this is just showing off the same thing that I've just spoken about. So this is just looking at a cubical graph. But yeah, I could call, is it a loop-free graph? Is it a directed graph? Etc. So this is not a directed graph. Cool. Right, so let's look at a little bit more like global properties of graphs. So, if you want to query whether two graphs are isomorphic, again, you're going to pull in one of these Q type functions, returning a Boolean. So these two graphs are isomorphic. And we can actually go ahead and use these built-in find graph isomorphism functions to actually identify the isomorphism involved in these two graph objects. So that's all pretty cool. So sometimes, in networks, it's kind of like, important to be able to identify the connectivity of individual nodes within networks. This can be kind of indicative of a bunch of different stuff. So if we have an individual graph object here of consisting of like two graphs, we can identify the connected components. If we then wanted to kind of like highlight those, we can kind of use highlight graph to identify. So we're highlighting the individual nodes and edges which are within the connected components here. Yep. Okay. So this is just looking at more examples of how you can get use that highlighted graph function. So here I've got a matrix. I am then turning it into a graph and then turning it into a throwing in some style options. And then I can go ahead and highlight that graph given these connected components coming from that graph here. Okay, also, might want to query measurements. So distances within graphs, we're going to use graph distance. So here I'm making two adjacency graphs coming from the matrix. I can then go ahead and use graph distance to work out the distance between two nodes. So what distance is chosen in the case of dual edges. So if you've got dual edges, then you're going to take the smaller version. Okay, so when you're using, let's have a look at these two graphs here. So going from 2 to 3. Within the weighted adjacency graph 2, I think you can't go from 2 to 3, so it is infinite. Yep. So yeah, this is querying the distance between 2 to 3, and so in this case, you can go, we can follow along from 2 to 4 to 3, which is, working out the weights. So here we've got 3 plus 3, so 6. But when we're looking at this graph here, it's a little bit different. Going from 2 to 3, there is no option to go that way because there is a directed edge from 3 to 4, aka which is kind of preventing our ability to go from 2 to 3. Ergo, we have an infinite. So it's effectively impossible to go from there. It is an infinite distance, so it's not possible. And then we can also just find, call graph distance for a given node to work out all the this is kind of like a listable function. So let's look at the attributes of this function. Okay, it's not quite listable. It's just protected. I think this is just plugging it in, kind of automatically mapping over this weighted adjacency graph here for a given node. Okay, so also we can handle large graphs in Wolfram Language. So let's pull in a large graph of some expanded genetic tree. Hopefully my computer doesn't slow down too much. It's somewhat struggling. Worst case scenario, I might abort that. Okay, never mind. Okay, let's pull in, yes. Okay, let's pull in an example graph. So here, just a genetic graph. I think that's working. Seems to be struggling. Okay, I'm just gonna, I've just overloaded the kernel a bit. Never mind. Okay, so we can pull in, again, like coming back to this example data, it's a powerful way to learn about different types of thing. Here, I'm pulling in just a large graph. When your graphs are quite large, it oftentimes won't try and render it automatically. Rendering enabled. It's just going to come up with this kind of like metadata about the graph, and it looks like it's kind of calling some of these built-in graph property functions. So it is not a directed graph or an acyclic graph. If you actually want to force the display of a large graph, you're going to have to call graph plot on it. Okay, so if you want to, let's go ahead and create a graph. Sometimes if you want to like label a large graph, it's often easier to kind of drop the labels altogether. And once it gets pretty big, it gets pretty messy to actually see anything. So that's why, if we're looking at this, I think this function here, word rules, is kind of generating similar words for a given step value of 1 to 4 to 1. So kind of like working out nearest related words in general. But basically, if you have large graphs, it's often easier to not show the labels because it's actually going to create complicated, it's computation expensive. So be aware of that. Okay, I should probably hurry up because I've got a lot of content to cover. Again, this is looking at a similar thing. Okay, we can also kind of like identify communities within graphs. So here I've got a kind of like pre-existing, I'm using this word rules to kind of create a bunch of information. So network. Okay, so yeah, similar words to do with network. Word rules. Ooh. What are we doing? We are kind of getting a bunch of, basically, yeah, just pulling in a bunch of random words or words related to that word. We can then like identify communities within those graphs. So this is kind of like grouping vertices into individual clusters, and then we're kind of creating a nice high level overview of information about the graph. So this is kind of similar to highlight graph, to be honest, kind of highlighting individual clusters within the graph. Okay, so we can also kind of identify subgraphs within Wolfram Language. So let's make another graph. We can then identify isomorphic subgraphs using find isomorphic subgraph. We can then highlight an individual subgraph using this nice highlight graph function. Again, if we wanted to find like a clique, so a subgraph which is actually already a complete graph, so each node has an edge to each and every other node, then we can also do that. Again, we can use highlight graph to use these subgraphs to identify the complete graphs within that graph object. So subgraphs and cliques aren't necessarily unique. We can kind of find all of those. So some of these are going to be the same. Yeah, I think that's just a reversal. But yeah, we can also kind of find every clique within a graph according to these parameters. So connectivity. So vertex connectivity of a graph is the smallest number of vertices whose deletion will lead to. So kind of like a heuristic of connectivity of a graph. So if we create this graph here, we can kind of identify how connected this graph is. So if we were to delete things within this subgraph, we would reduce the connectivity. So if we take a look at this kind of like subgraph here, so call the subgraph function on the connected graph with these individual nodes, which are kind of related to these ones. Then we can extract out the subgraph, or we can pass it through from a list of edges. It's a pretty versatile function. Or we can even pass it in a property or pattern even. So here within this graph object, we have a bunch of nodes which are blue. So if we pass in subgraph, kind of capture that within a pattern with a distinct kind of like condition on the condition that this pattern is equal to this RGB color. So I think this is just going to match that. So yeah, it's kind of like extracting out the individual nodes which are uniform with this color. So yeah, we can extract out the subgraph in a bunch of different ways, and now we have an increase in the subgraph, because if we wanted to disconnect the graph, then we have to delete 3. Whereas it's a bit different there. If we delete those 2, then we completely reduce the connectivity of the graph. So we can delete some of these graphs. So what does this look like? So we've deleted some of them, and then this kind of reduces the connectivity of the graph. And then the connectivity of this disconnected graph is now 0, because it is no longer connected. Some of the nodes are external to the rest of the structure. Okay, so we can kind of solve some graph theory problems in the Wolfram language very, very easily. So oftentimes, if we're looking at some ways of solving things, I think this is to do with the 4-color theorem. So at most, 4 colors are required to color any loopless planar graph, such that none of the 2 graphs are the same. I think it's shown nicer here. So we only need 4 colors to color in a map of the United States so that no two connecting nodes are touching the same graph. So with all that said, we can go ahead and create a mesh or a unique mesh according to these random reals. So this is just generating a bunch of random reals, which are just floating points in the Wolfram language. And then we are creating a graph from that mesh. And so we can kind of go ahead and use the planar or fine planar coloring to actually solve that problem, the four color theorem, for a given mesh which we've just created. So what does the graph look like? So that's the graph that we're working with, the one we've just created here. And then we've just kind of solved that for the four color theorem so that we don't have any more than four colors utilized within our mesh so that no two are touching. So basically this is just showing off that the power of the fine planar coloring, which is kind of solving a relatively complicated mathematical problem. Again, we can kind of do the same with dual graphs. So we can go ahead and extract out the graph that we were just using then. And then we can again go and kind of like augment that into a dual graph using dual planar graph. So I think this is every time there is a face, we replace it with a vertex. And then we can again call these similar functions to kind of find the planar coloring and then do the same thing so that we are, for each vertice, none of them are going to be connected to any colors of the same. So again, we're using the same amount of colors and there are no connecting colors of the same nature. So again, the same with edge coloring. It's relatively similar things. And then we're doing the same with our initial graph object so that no edges are the same color. So very high level functions being used here to solve some relatively complicated problems. So also, if you want to like look through, there are ways of solving complicated graph walk and trail type problems. So these can be done again as we solved our planar coloring type problems. We can solve our walk type issues using relatively high level functions. So Hamiltonian path, finds the Hamiltonian path with the smallest length. So this is kind of employing a bunch of the like algorithmic knowledge we've kind of amassed over 30 years to solve a relatively complicated problem with one function. So here we've made a Hedron graph. We can then just plug that to identify the Hamiltonian path with this single line of code. Then if I wanted to, I could just create a row of my initial Hedron graph. And then I'm highlighting using that highlight graph function on my Hedron graph, and then just creating a path graph. So taking the individual nodes and then identifying the Hamiltonian path, and then kind of like coloring that in to identify that. So very cool way to solve things. As you become more aware of general Wolfram language functions, you can like solve problems with like you can identify the correct function to use at a given scenario. So very worth being aware of all of these. Again, Hamiltonian cycle, identifying the same thing but within a cycle, and we can do that as well. Also, we're not limited to Hamiltonian paths cycles. We can also identify Eulerian cycle. So here we've taken a graph. We can then just call that function and then kind of like plot that using this. I think this is predefined later on in the graph in the notebook. So if you want to see how that's done, it's very cool. This is probably using some kind of manipulate function, which is a pretty powerhouse function for if you want to show off cool interactivity within the Wolfram language. Also, so we can like kind of solve the traveling salesman problem. So we're kind of getting a Hamiltonian cycle. So visiting every single vertex once and start and end at the same place. So we can use this with find shortest tour. So let's make a weighted graph. And then, yeah, we can identify the shortest tour with just a single function. Think, what methods are these using? Method. But yeah, there's a bunch of different, I think you can specify the method. So let's have a look at this. Okay, so we can use all tours, greedy. Presumably that's going to be different every time. Or maybe that was just the automatic one. Or they might just be finding the same result. But yeah, you have this like interoperability for find shortest tour. Maybe this isn't the right example to show different methods. Cool. Also, we can solve things like Chinese postman problem in relatively simple amount of code. So again, let's make a graph, and then we can just find postman tour. So again, high-level function, high-level specialized function. So you know, Wolfram language, we have about 6,600 functions. The chances are that one of those functions is going to be a very high-level way of solving a distinct mathematical problem, or you know, anything kind of within the realm of computer science in general. Again, we can use this like kind of built-in path animator, which is defined later in the notebook, if you want to check that out. And I think this is just, you know, animating the individual path someone would take to find the postman tour for the Chinese postman problem. Okay, also, you know, we can kind of do things to solve mazes. So here we've set up a maze. We can then find the shortest path using the find shortest path algorithm. And then here we get a solution. Then we can go ahead and show that off in this nice format here. So here we've just solved a maze. And then we're just showing off. So show was kind of like layering over two graphical functions together. So yeah, you can kind of like layer them together. Also, so we can look at the, you know, graph distance of our, you know, the start and the end. Okay, we can also do stuff with flow networks. I think I'm gonna skip this one, let you guys look at this at your own time. Okay, so I guess in general, like stuff to take away is that, you know, in Wolfram language, you know, you have this like nice symbolic way of representing graphs. There's a bunch of different ways that you can create graphs, and it's all very, you know, interpretable. So you don't need to like stress too much about particular graph formats. You can kind of, you know, it's very, very flexible in that sense. So you can kind of you can use these very basic, I guess not basic, like kind of abstract concepts to represent a huge amount of things in you know, the world, society. If you want to like get a better understanding, do some modeling of things, it's a very powerful thing to be aware of. You can represent it in many different ways. So the nice thing about Wolfram language, you kind of have these built-in graph algorithms that you can kind of assess your graph in unique and distinct ways. You've got hundreds of different functions to be able to do so. You know, you're not limited by graph types. You can use direct graph, undirected graph, weighted graphs, and these are very interoperable with matrices. Also, you can kind of import many, many different types of graph format. So that's all very good.